Dear students, welcome to EPG Pathshala. During this session, we will discuss about acids and bases, factors affecting acidic strength, conjugate acid-base pair, theory of indicators, and acid-base titrations and applications of acid-base titrations. Various concepts of acid and bases includes Arrhenius concept, Bronsted-Lowry concept, and Lewis concept. According to Arrhenius concept of acid and bases, those are the acid which can provide proton or H positive in the aqueous solution, they are acid, and the bases are those which can provide OH negative to the aqueous solution. According to Bronsted-Lowry concepts, all the acids are those which can provide H positive to the aqueous solution. That means all the Arrhenius acids are Bronsted and Lowry acids, but Bronsted and Lowry bases are those bases which can accept an electron, which can donate an electron pair, but they may or may not be proton donor. That means all Arrhenius bases, they are not Bronsted bases. Lewis concept is the wide concept. According to Lewis concepts, all electron donor, they are bases, and all electron acceptor, they are acids. Conjugate acid base pairs. A conjugate base is formed when an acid loses proton, and a conjugate acid is formed when a base gains a proton. A conjugate acid base pair is a pair of substance that differ by one proton only. For example, HCl plus water, it will give, in this case HCl is an acid and water is a base, and the conjugate base for the HCl acid is chloride, and conjugate acid for water is H3O positive. Various factors affecting acidic strength are bond strength. A stronger bond is less likely to break. Bond strength decreases as we move down a group in the periodic table, so acidic strength increases. Stability of conjugate base. Carboxylic acids are typically weak base, means they can only partially dissociate into H positive and RCO negative in neutral aqueous solution. The strength of bases and acid is shown in this figure. As the acidic strength increases, comparatively the base strength or conjugate base strength, it decreases. All the strong acids, they have weak conjugate bases, and weak acids have strong conjugate bases. Equivalent point versus end point. During an acid base titration, the point where indicator changes color is often described as end point of the titration. End point of the titration is usually the visible point of where the color change is observed. Ideally speaking, the color change would happen when two solutions are mixed in equal proportion. This point is known as equivalent point. The solution must be neutral at this point, but it may or may not happen. For example, in case of titration of ammonia solution with HCl, this titration will result into ammonium chloride. The ammonium ions are slightly acidic, so pure ammonium chloride is slightly acidic at equilibrium point. Titration errors with indicators. There are two types of titration error in acid base indicator. Determinant errors are that occur when pH at which indicator changes color differs from the pH at the equivalence point. It can usually be minimized by choosing the indicator carefully or by making a blank correction. So, this slide shows the difference between good endpoint and bad endpoint, because in the bad endpoint the solution is over titrated, means extra amount of base has been added to the solution. An indicator is a reagent or device used to detect visual color change when reaction is quantitatively complete. Acid base indicators are weak organic acid or bases possessing different colors depending upon the H ion concentration. This table shows that thymol blue, the pH range for thymol blue is 1.2 to 2.8 and the color in acidic solution is red and the color in basic solution is yellow. Methyl orange, pH range is 2.7 to 4.7. The color in acidic range is red and in basic range is orange. Methyl red, the pH range is 4.2 to 6.3. The color in acidic range is red and basic color is yellow. Phenolphthalein pH range is 8.3 to 10 and it is colorless in acidic solution and pink in basic solution. Acid base titrations in aqueous solution are based on reaction between hydrogen and hydroxyl ions to form water, which is ionized to very small extent, H positive plus OH negative H2O. The reaction of a solution by their negative logarithm rather than actual concentration of H ion or OH ions. Generally, hydrogen ion concentration is expressed in terms of pH. pH is equal to log 1 divided by H ion concentration. It is equal to minus log H ion concentration. pOH is equal to log 1 divided by OH ion concentration is equal to negative log OH ions. pH plus pOH is equal to 14 in neutral solution. Strength of an acid and base is relative to proportion of which it has reacted with water to produce particular ion. For example, if some strong acid is added, H ion concentration will increase and pH will decrease from 7 and if some base is added to water, the pH will increase and the OH ions are added to the solution. The concentration or the strength of acid may not be correlated to strength of acid and concentration are not related. For example, strong acid may be dilute in terms of concentration. Titration curves for strong acid versus strong base. Titration of HCl versus NaOH falls in this category. Using a pipette, pour 5 ml of 0.1 normal HCl solution into flask. Add 3 drops of phenolphthalein indicator. Fill up the burette to 0 mark with NaOH. Titrate 0.1 normal HCl solution with NaOH from the burette. The solution will turn its color to pink when the equivalence point is reached. Repeat the titration 3 times and notice the volume of NaOH used. Count the arithmetic average of volume and calculate the exact NaOH concentration according to the equations given below. Acid to alkali solution. From the figure or from the graph of pH versus volume of acid added as the acid to alkali solution. From the figure it is very much clear that pH only falls a very small amount until quite near the equivalence point. There is the sharp decrease, the pH falls all the way from 11.3 when you added 24.9 ml to 2.7 when you have added 25.1 ml to the 25.1 ml of acid to the solution. Alkali to acid titration. This is a very similar to the previous curve except that the pH starts off low and increase as we add more and more sodium hydroxide solution. Common ion effect. Common ion effect is an application of Le-Chatelier principle that depict the change in equilibrium position due to addition of an ion already involved in equilibrium process. For example, acetic acid plus H2O will give you hydronium ion plus CH3CO negative acetate ion. Addition of sodium acetate solution will shift the equilibrium towards right due to excess of acetate ion. This will decrease the concentration of H3O positive. Solutions containing a mixture of acetic acid and sodium acetate are less acidic than those solution of acetic acid alone. They are less basic than those of sodium acetate alone. Applications of acid-base titration. Determination of acid neutralization capacity of antacid tablet. The pH of stomach is acidic for proper digestion of food. The increase in acidic level of stomach creates discomfort. The antacid preparations are basic in nature, made from metal hydroxides, metal carbonates or mixture of two. The acid neutralizing capacity of a tablet is the amount of HCl that it can neutralize. This capacity can be determined by a technique called back titrations. The figure shows the pH of stomach and effect of sodium bicarbonate and other antacids, which includes calcium carbonate, magnesium hydroxide, aluminum hydroxide on the acid present in the stomach. Determination of antioxidative abilities of vitamin C and selected infusions. Antioxidants protect our body from free radical action. They are present in herbs, coffee, tea, cocoa and other plant products. Plant extracts rich in polyphenol and flavonoid reveal strong antioxidative properties connected with the presence of several hydroxyl groups. Procedure: weigh the vitamin C tablet and grind with pestle mortar. Add the tablets to flask with some distilled water. Wash any remaining solid into the flask. Add water to make final volume 100 ml. Stir the solution for a few minutes. Add a few drops of phenolphthalein indicator solution. Begin the titration with NaOH again. After the end point is reached, record the volume of NaOH used. Re-acidify with 10 ml of 1 normal HCl again and add 3-4 drops of starch solution. Begin titrating with sodium iodide solution. Record the volume used. Repeat the above steps with other tablets to compare the antioxidative abilities of different tablets, and you can compare the values written on the tablet and the tablet itself. Determination of acetic acid in vinegar. Pipette out exactly 5 ml of commercial vinegar sample into 250 ml flask and add 100 ml of distilled water. Add 5 to 6 drops of phenolphthalein indicator. Then titrate the acetic acid solution with standard NaOH solution to pale pink equivalence point. Record the burette readings. Repeat the titration twice more using fresh aliquot of vinegar. Calculate the percentage weight by volume of acetic acid present in the vinegar. Alkalinity of water is determined with the help of acid-base titrations. Basically, alkalinity of water is its acid neutralizing capacity. It is sum of all the titrable bases. The measured value may vary significantly with the endpoint pH used. Alkalinity is measure of an aggregate property of water and can be integrated in terms of specific substances only when chemical composition of sample is known. The procedure includes that sulfuric acid should be taken into the burette, and before starting the titration, burette should be rinsed. Fill the burette with sulfuric acid and take sample 20 ml or 100 ml of sample, pour it into the flask. To this, add few drops of phenolphthalein indicator and titrate it with sulfuric acid. when you add phenolphthalein to the solution, the color of solution becomes pink because of the presence of OH ion. And as you go on adding acidic solution to the sample, the color of solution becomes solution become colorless at the end point, and this end point gives the OH alkalinity, but the solution contains OH carbonate as well as bicarbonate alkalinity. In this case, you have to start the titration again, but with another indicate. The second indicate to the sample, add second indicator, that is mixed indicator. Now this indicator is for determination of carbonate and bicarbonates. Start the procedure or start adding sulfuric acid from where you have stopped the first titration. Now the solution will become blue to red. This is for bicarbonate and carbonate alkalinity, and this will give you the total alkalinity. Second titration will give you the total alkalinity from the volume of sulfuric acid. Now calculate the alkalinity with the given equation. Dear student, during this session we have learnt about various concepts of acids and bases, theories of indicators, acid base titrations, and various applications of practical importance of acid base titrations, including determination of neutralization capacity of antacid tablets, antioxidizing ability of vitamin C, alkalinity of water, and strength of commercial vinegar available. Thank you, students.